Hello, my name is Hadi Farhangi. On Basics of Statistics, Confidence Intervals. Topics of this video: first introduction, then central limit theorem, then confidence interval for the population mean, confidence interval for population mean when population variance is known, confidence interval for mean when population variance is unknown, and some examples related to. First topic, the introduction. A normal variable has a symmetrical distribution and it is shown with n mu sigma square. Mu is mean, sigma square is variance. If x is normal with the mean mu and variance of sigma square, then x minus mu divided by sigma is a standard normal. Relation between alpha and z alpha. Probability of z less than equal z alpha is equal to alpha. And z alpha, you can use function norm dot inverse alpha 0 and 1. Relation between alpha and t alpha is that probability of t less than equal to t alpha is equal to alpha. And you can find t alpha by the equation t dot inverse alpha and nu. Alpha is probability, nu is variable x may have some distribution with some mean and variance. Then what one may say about the distribution of Xbar. This chapter explores central limit theorem to answer to this question. This chapter also constructs a confidence interval that the population parameter belongs to with the probability of 1 minus alpha, where 1 minus alpha is the confidence level and alpha is significance level. Note that the confidence interval can be created for mean, variance, proportion, correlation, regression, etc. This video focuses on confidence intervals for means. When calculating z alpha and t alpha, consider their absolute values in this chapter. Sometimes they can be negative, but we have to consider their positive value for the purpose of this chapter. Central limit theorem. While taking a sample of a variable that is either normal or if sample size is greater than equal to 30, then the mean and variance of samples are expected to be mu and sigma squared to n. That means x bar should be mu and variance of x bar sigma squared divided by n. The mean of sample is expected to be normal as with the mean mu based on part 1 and variance of sigma squared over n. Example, a sample of size 10 is taken from a normal distribution with a mean 150 and variance of 25. What is the expected mean and standard deviation of this sample? So based on central limit theorem, since variable is normal, one can use central limit theorem. It follows that the mean and variance of the sample will be x bar equal to mu, that means x bar is 150, and sigma square of x bar is sigma square divided by n, 25 divided by 10, 2.5. That means sigma of x bar, standard deviation of x bar, is the square root of 2.5, which is 1.58. Here's another example. A sample of size 100 is taken from a distribution with the mean 200 and variance of 16. What is the expected mean and standard deviation of this sample? Answer. Since sample size is 100 greater than 30, one can use the central limit theorem. It follows that the mean and variance of the sample will be x bar equal mu. That means x bar is equal to 200. Sigma square of x bar is sigma square divided by n, 16 divided by 100, which is 0.16. And the standard deviation of that will be a square root of 0.16, which is 0.4. Next topic, confidence interval for population mean or mu. An example of interval is brackets 15 and 20 that shows the range that parameter can vary. In this example, 15 is the lower bound of interval and 20 is the upper bound of interval. A confidence interval is an interval that the parameter belongs to with some probability. For example, one may say that the mean of variable belongs to brackets 120 with probability of 90%. So brackets 120 becomes a confidence interval. A confidence interval for population mean is an interval such that brackets LB and UB that the mean of population belongs to with probability of confidence level, which is 1 minus alpha. In other words, probability of mu between lower bound and upper bound will be equal to 1 minus alpha. If central term conditions are met, one may write x bar is normal with the mean mu and variance of sigma square over n, and probability of mu between minus z alpha divided by 2 and z alpha divided by 2 is equal to 1 minus alpha. One can find 1 minus alpha confidence interval as follows. Mu is between x bar minus z alpha divided by 2 times sigma over square root of n as lower bound, and x bar plus z alpha divided by 2 sigma over square root of n as upper bound. Or you can put them in the bracket, and mu belongs to this confidence interval, the confidence level 1 minus alpha. And here's the proof that how the confidence level is derived, and you can look at it and see it for yourself. Next, confidence interval for mean when population variance is known. The left tail confidence interval is mu less than equal x bar plus z alpha times sigma over square root of n, or you can put them in the bracket, minus infinity to x bar plus z alpha sigma over square root of n. Right tail confidence interval is at x bar minus z alpha times sigma over square root of them, n less than equal to mu, or you can put it in the bracket. Two-tail confidence interval, as I showed in previously, is between x bar minus z alpha divided by 2 sigma over square root of n and x bar plus z alpha divided by 2 sigma over square root of n, or you can put it in the brackets. Confidence interval for mean when population variance is unknown. So when from known variance we go to unknown variance, you have to use t distribution. So instead of sigma, we have s, and instead of z, we have t. So left tail, just z changed to t and sigma to s, and pretty much everything else is the same. For the right tail, confidence interval, the case of variance is unknown, is the same thing, and you can put that in the bracket. And in the bracket case, x bar minus t alpha s over square root of n to infinity. For the two-tail case, we see the same thing. Lower bound x bar minus t alpha divided by 2s over square root of n, lower bound, and upper bound x bar plus t alpha divided by 2s over square root of n. So sigma is changed to s, z alpha to t alpha, z alpha divided by 2 by t alpha divided by 2. And beware that in the two-tail case, we use Z alpha divided by 2 and T alpha divided by 2. Next topic, examples, confidence interval for mean or mu. We are going to create confidence interval for mu. Example, consider variable x that has a standard deviation of 30. A sample of size 25 is taken that has a mean of 210. A, construct a 99% confidence interval for the mean of variable x. B, construct a 95% right tail confidence interval for the mean of variable x. C, construct a 90% left tail confidence interval for the mean of variable x. And here's the answer. Here are the available information. Sigma is known, 30, Xbar is 210, and n is equal to 25. Summary of the question. Since sigma is known, a standard normal should be used in all parts. Part A, two-tail confidence interval with confidence level of 99% should be created. This means 1 minus alpha is 0.99 and alpha will be 0.101. For the two-tail interval, Z alpha divided by 2 is equal to 0.01 divided by 2, or Z of 0.005, which is 2.576. One can substitute all these values in two-tail interval. I have the formula for the two-tail interval on the top. We substitute all these values that we know inside the formula, and after all the calculation, mu will belong to the interval with the lower bound 194.5 and upper bound 225.5. Part B, for the right tail confidence level, it is 95%, 1 minus alpha 0.95, which means alpha is 0.05. For the right tail interval, Z alpha is Z 0.05, which if you use software, it is 1.645. One can substitute all the necessary values in the right tail interval. This is the formula in the first line, Xbar minus Z alpha sigma over square root of n. And if we substitute all the values, mu will belong to the lower bound 200.13 and upper bound infinity. For part C, left tail confidence level is 90%. This means 1 minus alpha is 0.9. That means alpha is 0.1. And Z alpha is Z of 0.1, which is 1.28. The left tail confidence interval, first line shows that X bar plus Z alpha sigma over square root of n. If we substitute all these values that we know inside this formula, the mu belongs to the interval of minus infinity to the upper bound 215 to 217.68. More examples. Consider the following data. Construct a 95% confidence interval for the variable customers. Here's the data. There are 5 days and the number of customers in each day has been recorded over here. Obviously, we don't have any information. So sigma is unknown. We have to use T and S. Here's the answer. Since variance is not known and only data is available, one should use T distribution and calculate S. First, one should calculate S. There are 5 observations n equal to 5, and sample mean is X bar equal to 30. X is variable customers. And here's the table I use to calculate variance. The deviation from the mean in the second column, and in the third column, that deviation, that distance is squared. And S squared will be the summation of the last column divided by n minus 1. and it will be 52 square, so variance is 52 square, and S is equal to 52. The confidence level is 95, which means 1 minus alpha is 0.95 and alpha 0.05. Also, T alpha divided by 2 and nu is equal to T 0.025 and nu is equal to 4. If you use software, it will be 2.776. If you substitute all these in two tail confidence interval, you will get mu belongs to the lower bound 235 and upper bound 365. And we have X bar, it is 300. We have T alpha divided by 2, which is 2.776. We calculate S is 52 and N is 5. So if you substitute all these values, I showed all the steps in the calculation here, you can repeat and see for yourself.